So we're going to continue with work problems, work done by pumping a fluid out of some container or into some container. So in this case, we're trying to find the work, pump all the water in this weird looking shape out the top edge. So the dimensions are given, height of 3 feet, across top of 4 feet, and a depth of 6 feet. Now I've given that a little bit more of a profile look in my rendering, because typically what you want to do with these problems is work with a horizontal slice and figure out, well, what's going to happen when I move that slice. So let's find that. Let me just draw a little slice through here. And short it up a little bit. That. Oh, didn't work. Here and here. So there's our little slice. I want to find what happens when this slice goes all the way through our region. So the first thing we want to do is want to calculate the force on one slice. So force on one slice. And the force required is just really going to be the density times the volume of that slice. And the volume can be further broken up into the area times the thickness. So, okay, let's see about orienting ourselves in this graph a little bit more, try and draw some things and see if we can't reach some conclusions. I'm going to start by putting 0, 0 down here at the bottom. So that's the base of my figure. And if I did that, what's going to be up here at the top? What are the coordinates there?
0, 3.
0, 3, thank you. 0, 3. Now over here, I also get coordinates. Since I'm at a height of 3, that doesn't change. But what changes is the x coordinate. Now I'm over at 6. So 6 and 3. And this point here in the middle, I'm going to give it general coordinates of x and y. Okay. Well, let's take a look at our slice first of all. The slice is taken horizontally, so that means it has a dy thickness. So dy is my thickness. And the area, well, when I slice through this, if I take a little thin slice, the area is just going to be the area of a rectangle, right? Because this shape is going to go back along here. So you're just going to have a rectangle. So what are the dimensions of that rectangle going to be? Well, in one direction, it's going to be x. You can think of it as x minus 0 if you'd like, but it's just going to be x. And in the other direction, it's going to be 4. So it's going to be x times 4 or 4 times x, whichever way you want to slice it or whichever way you want to write it. Now, being consistent with what we did in the rest of chapter 6, you might notice that here I've got an x and here I've got a dy. That doesn't work too well. You've got to have the same variable for both of these things. So let's take a closer look at this and realize that this point is on the line that connects these two. So we can find the equation for that line. A lot of you could probably just look at it and blink and maybe see that equation, but let me actually be very careful in demonstrating where that equation would come from. The first thing I'm going to do is I'm going to find the slope of the line. So I'll take y2 minus y1, so 3 minus 0, over x2 minus x1. So I get 3, 6, which is 1/2. Okay. And then I'm going to drop it into an old familiar favorite. It is y minus y1 equals m times x minus x1. My son's calc teachers seem to always avoid this one, and I hated it. But you're free to do other things too to find the equation of the line. If I drop in one of these points, it doesn't matter which one, so let me choose the easier one. I get y minus 0 equals 1/2 times x minus 0. Basically, y equals 1/2 x. Yay, that's good. Except for one thing. I need to solve for x. But that's pretty easy. Multiply both sides by 2, and I've got my substitution for x. So 2y equals x, and that goes in here. So it's going to be rho times 2y times 4 times dy, or in other words, 8 times rho times y dy. So that's the force required to move one slice. Okay. Are you comfortable with how we got that part? That's a hard part. I think the last time we did stuff like this, I set up little milestones for you. If you get here, that's a milestone, all right? That's worth some points, is getting this expression. Let's come up with another expression. That other expression is the distance. Well, distance, like before, is going to be top minus bottom. So top minus bottom. The top of this is at a height of 3. And this slice is at a height of y. So 3 minus y is the distance that it moves. So that's another little milestone in this problem. We can put those things together now. I've got the force, I've got the distance. I can calculate the work to move one slice. Work to move one slice. So work is going to be force times distance. So it's going to be 8 times rho times y times 3 minus y. And I'm going to put the dy at the end, just out of convenience. If you wanted to, you could distribute the y. 8 times rho times 3y minus y squared dy. Okay. Almost done. That's the work done to move one slice. Let's see about finding the work done to move all such slices. So for that, I'm going to integrate. I'm going to take the 8 and the rho outside. 3y minus y squared dy. But the problem that I have to figure out now is, what are my limits of integration? So what am I going to integrate to and from? John? What do you think I should use for my limits of integration?
Is it 0 and 3?
Perfect. 0 to 3. Because 0 is as low as I can go in my region, and 3 is as high as I can go in my region. So, yay. If rho is 62.5, that'd be pounds per cubic foot. 8 times 62.5 is going to be 500. 0 to 3, 3y minus y squared, y. Can we jump to the happy ending from here? You need to see the details? $2,250, and the units would be foot-pounds. Okay.
Hey, Jeff.
Yeah.
Quick question. On a test, for example, where do you want us to stop? Do you want us to like finish that off basically with all the math, or just stop here and plug in the calculator?
I'm not really big on you guys doing a lot of this stuff, finishing off this grunt work by hand. I mean, I think that most people are pretty decent at it. And if you're going to make a mistake, I don't want to take off points because you made an arithmetic mistake. I want to grade you on calculus, not arithmetic. So I'm not going to be big on you guys always evaluating these things. There might be a couple trig integrals that I'll ask you to finish up, just because you can't get an exact answer out of, Desmos, or your graphing calculator is just going to give you decimal approximations. And so sometimes for those, I might ask you to finish up by hand. But a lot of these, look, these problems take a long time, and I don't want to make that even longer by asking you to do a lot of trivial calculation at the end here. So yeah, these, I'll probably tell you in certain problems, finish it up with FN int.
And also for the beginning of the problem, when you got x times 4, could you just show that visually to us really quick?
Sure. So visually speaking, what's going on is that this slice really has an area to it. So if you were to look at that slice, we're actually calculating the volume of that slice. So the volume of a box is the height times the width times the depth. It's those three measures, right? So the height here was just your dy. That was the height of this. The width, well, I called that x. I just put a general point there, called it x. And then the depth here was that distance across the figure this way, which is 4. So it's really just the area of a square, or area of a rectangle, 4 times x times the height, which is your dy.
Gotcha.
And then what we did is we calculated a relationship between these 2 points, gave us the equation of a line, and allowed us to substitute an expression for y in for x, because I needed to have both of these things done in terms of y. They all had to be done in that variable. All right. How's that one looking? Okay.
What exactly is dy?
What's that?
In that picture,
Yeah.
what would be dy?
So good question. dy, let me see if I can't squeeze it in for us right here. Let's do it this way. So the height here is 3 feet, but dy is just the thickness of that slice. Now, technically, if you were taking more care than I am, it's a delta y, and then you're going to add up the volumes or with a Riemann sum. But to get a better and better approximation, you're going to take the limit as those slices get even thinner and thinner and thinner. And in the limit, that delta y becomes a dy term. So I just kind of jump right there. I'm like, okay, horizontal slice, that's dy. That's the height of this. It's the differential. I don't think we really teach that, the meaning of this exactly anymore, but it's just our little shorthand notation for the thickness of that slice. Does that help
Okay.
out?
Yeah, and then also, why exactly, what was the purpose of finding M?
Finding, oh, the slope. I needed the equation of a line between these 2 points because that gave me a relationship between X and Y right down here that I could use in finding the expression here. Because at one point, I was stuck with a force that involved X's and Y's. But I know from experience that I better have it in one variable, and it better be this variable. So I changed over the X to an expression involving Y. So that's why I needed the equation of the line there, is to have a relationship between those 2 variables.
Okay.
Okay, we'll see that again. We're gonna do one more problem like this. Yeah, so I'll tell you what I'll do. I'm gonna do one more problem like this. I'll put this one, which I did out and getting ready for today. I'll put this one in the notes, but I wanna do one that involves kind of a sphere. This shape is called the frustum of a cone. So let's take a look at that one. I think that one should be on your little handout there that I sent you. Is that true? We've got this on our handout?
It is.
Yeah, we do.
Okay, good. So I'm hoping that'll make it a little bit easier for you to work with and draw. In fact, I'm going to sketch out as best I can that figure. I'll leave this up as long as possible while I sketch. That way, that way you won't laugh at my sketches too much. All right, so let's take a look here. There. So although it's a little exaggerated, this kind of looks like the shape of a lot of glasses. And one time was a bar in Royal Oak. It used to be called Woody's. Now it's Hot Cat. But on the roof, they didn't want you to have glasses, actually glass glasses. So they gave me a plastic cup. And beer snob that I am, I really resented my beer in a plastic cup. And then I started looking at it, and it just really didn't look like a pint of beer. And so I actually took it home and measured it and calculated the volume, and it turned out to be exactly 1 pint of beer. But, all right, so let me cut over to here. Let's see, I need to grab a few dimensions first. 0. So let's see, 6 and 12 would be the radius of the bottom and the top, respectively. And this is in units of meters. No, this is still in units of feet. All right, never mind. Meters, no, feet. And a height of 21. Okay. So here's my little drawing. Nothing too spectacular for sure. We're going to pump water out of the top edge of this thing. So it's nice to know that it's 21 feet tall. It's a huge tank. Not sure why I'd build something quite like this, but whatever. Let's just work on the math and see if we can't find the force on one slice. force on one slice. Now, as you make a horizontal cut through here, you should probably draw maybe a little bit of a curve. And something like that. Now our horizontal slice is going to have a dy thickness again. We'll give this point some general coordinates of x and y. Let me give myself some more coordinates. I'm going to put 0, 0 at the center in the bottom. And because this is 6 feet wide, that will give this coordinates of 6 and 0. Likewise up here, if I went straight up 21 feet, I'd have coordinates of 0 and 21. And 12 feet out to the right, I'd have coordinates of 12 and 21. So there's our picture. Doesn't have to be all that good, just has to be good enough. And we're definitely on the good enough side. Well, I always like to start out by reminding myself that the force on one slice is simply going to be the density times the volume of that slice. And density of water is given to us at 62.5 pounds per cubic foot. So let me write that off to the side here, and maybe up top. Rho equals 62.5 pounds per cubic foot. Volume is just going to be the area of that slice times the thickness of that slice. Okay. What's the area of that slice? When I take a horizontal cross section of this figure, what's that area going to be?
Pi r squared.
Pi r squared. Good. It's a circle. And the thickness? Who's got the thickness for me? Rochelle? Oh, okay, go ahead. Rochelle? dy. Good. Thickness would be dy. And so now I'm left with figuring out what the radius is. Well, and I've given my point, or given myself some general coordinates on this figure. I could have put it over here, here, it doesn't matter. But the distance here from our center line to the edge is going to be x. X minus 0. So, okay. We need to figure out the radius. X minus 0. Just x. But I can't plug it in for the radius because I need this as an expression for y. So here's where I get to have some fun. I've got to find the equation of a line between these 2 points so that I have a relationship between x and y. Somebody asked a question about this earlier, so we're doing the same thing again. We've got to find a relationship between x and y so that I can write this as something depending on y. So this is where I'm going to find the slope again. Now the points that I want to look at and concentrate on is this one and this one. I want a relationship between these 2 points. So that's going to be 21 minus 0 over 12 minus 6. Or in other words, 21 over 6, which reduces to, let's see, divide 3, both sides, it's going to be 7 over 2. So that's the slope. Of course, keep in mind I'm not done. I need to find the equation of the line. And the equation of the line is going to be y minus y1 equals m times x minus x1. Well, I'll use this. This one looks simpler, right? That's my x1, y1. I'll plug it in here. Y minus 0 equals 7/2 times x minus 6, which is y equals 7/2 x minus 21. Now that's pretty good, but it's not quite what I want yet. So I got to have y solved, or x solved for, not y solved for. So let's see if we can't solve for x. I'll move the 21 to either side, y plus 21, and then multiply both sides by the reciprocal. So that's 2 over 7 times y plus 21 equals x. Woo. A lot of work to get that expression for x. But that's what we wanted right there. And now we can put that in here. That equals 2/7 times y plus 21. And then I'll put that up here. Let me pause, let you catch your breath. Maybe take a hit off the oxygen bottle. We're okay so far.
So that function you just did, that's like the side of that shape, right?
Exactly. Exactly. So that tells me how far out that is. And that's gonna change depending on the height. Is going to change the value of x, or the value of x changes the value of y. But in this case, we wrote it as
where to
x
find that?
depends on y.
Kind of like what points to use for that?
Well, I had to figure it out, right? Because they didn't give us that stuff to begin with. So if you look back at the graph here, or the chart that they gave us, they told us what those two values of r were, right? 6 and 12.
Yeah.
Agree? All right. So let's take a look at what I did here. So I started out, I said, okay, I'm going to make the center of my glass the point 0, 0. If the bottom has a radius of 6, that means if I move straight to the right from the bottom, I've moved a distance of 6. So that gives me coordinates of 6 and 0. The top had a radius of 12. Now, since the top was 21 feet above the bottom, if I move 21 feet straight north, I'm changing the y coordinate. So that made that 0 and 21. Do you agree with that?
Yeah.
Okay. And now from the top, if I move 12 feet to the right to get to the edge, I'm changing the x coordinate. So 0 plus 12 gave me that one. So that's how I got those two coordinates, is I had to kind of orient myself on this graph and then figure out what those two coordinates would be. So good question. And I hope that helps out, because you guys are going to have to do this for yourself a couple times. Set up some coordinates for yourself. Now you could choose different coordinates. You could make this the point, 12 and 21 if you wanted to, but then everything else would have to change accordingly. So the easiest thing to do is to start with a nice, easy point for 0, 0, and then build everything around that, which is what I did.
Right.
The equations will be easiest if you start with the 0, 0 at some point. Thank you.
Okay.
Hope that helps. Let's finish this up. Let's see. Okay, so we can put this in for R. And we get rho times pi times 2/7 times y plus 21 squared times dy. So that's the force on one slice. Now, let's think about the distance. And once again, having a nice orientation on these things helps out. So distance, as usual, is going to be top minus bottom. Let's look at our top coordinate. Our top coordinate up here is, well, the y coordinate anyways, is 21. Minus, well, the coordinate on our slice is just a y. So 21 minus y. And I'm going to put these two together. I've got my force on one slice, which is this. And then I've got the distance that it moves, which is this. If I put those two together, I can find the work done in moving one slice. Work done moving one slice. So that's going to be work equals force times distance. Rho times pi times 2/7 y plus 21. Now notice the square goes outside the second parenthesis. Rho times 21 minus y. And I took the liberty, oops, sorry, I ran off here. So I took the liberty of just rearranging the dy term to the very end. So something like that. Beautiful. Now I'll finish it up. Let me clean this up a little bit. If I square that out, that's going to be 4/49. So this is going to be rho times pi times 4/49 times y plus 21 squared times 21 minus y dy. Should probably put the 4 out there. Actually, 4 times 62.5 is going to be 250. So let's remind ourselves that rho equals 62.5 pounds per foot cubed. So 250 pi over 49 times y plus 21 squared times 21 minus y dy. I'd rather clean it up here than a little bit later.
Jeff,
Yeah, please.
why is this squared still on the y plus 21? Oh, never mind.
Okay, good. Yeah, so each of these gets squared, and I squared that and just brought it out front, but I couldn't replace that with some nice, easy numerical values. Yes.
Sorry, where did the x and the 21 minus y come from? Was that from simplifying it?
No, it's just a times. Because I ran out of room here. Let me write a little dot. That might be less confusing.
Yeah, I was like, thank you.
Yeah, it's a times here. So, my bad. All right. Now, these slices can be taken anywhere in this region. So in order to find the total work done in emptying this by pumping it out the top here, then we're going to have to integrate from 0 all the way up to 21. One thing to keep in mind, sometimes there's a couple places where you're going to have a figure where the spout is higher than the top edge. So like in the bonus one that I'll put in the notes, the spout is higher. It's 2 feet above the top edge. So the top edge is at y equals 4. The spout is at 6. So that means your distance is not going to be 4 minus y. It's going to be 6 minus y. Now in our case, because we're moving to the top edge, it's just 21 minus y. But you could easily imagine something being pumped out at a higher level. It's just going to depend on the problem. So just kind of a heads up there. Like I said, I'll put that extra example in your notes. Let's finish this up. 250 pi over 49 times the integral from 0 to 21 of y plus 21 squared times y minus 20, or excuse me, 21 minus y. 21 minus y dy. And that turns into, where was it? It's 900 some thousand, I think. Where'd it go? There we go. Now, again, be careful. I think they left their answer units of pi on WebAssign. So let's just take a quick look back here. Yeah, if take a look, they just leave the units of pi there, which is like, oh, really? I didn't see that, but that's what they do. Sorry. Keep on hitting the wrong one here. There we go. So keep the units of pi here, 909,000, 562.5, 62.5 pi, and the units would be foot-pounds. Whew.
Well, that was an easy problem.
Yeah, the good news is that I only put like 8 or 9 of them on an exam, so it should be no problem. Oh, you know what? I had to move locations here. I forgot my easy button downstairs. I'll have to get it though. All right. Anything on this one that you want further explained? I know that, you know, they're somewhat easy, but I can certainly understand you getting a little turned around at one place or another. And if there's something I can do to help, let me know.
In the figure above, in the main picture, I guess, you're saying if there was like something higher that the water would come out of,
Right.
would that have its own like volume also? We have to figure that out also, or
No, you know, I've never really actually been able to reason out that part of it, but really what's going on is that you're moving, you know, one way or another, that volume is getting moved up to that point. And that's all you have to worry about is the distance, okay? You know, the force required is still going to be the same. It's your, you know, same force, you're just moving at a different distance. So when you have something that's not the height of the lid here, you just got to account for that extra distance. So in this case, it'd be 6 minus y, as opposed to 4 minus y for the top edge. That's going to mean a lot more work moving it that extra distance. So, yeah, but I'll put this one in the notes. Oh, another good thing about this one is that it works in metric units. So the examples we've done so far have been in English units. Just a heads up on that. A nice way to kind of keep track of things is to use the density as 9,800 newtons per meter cubed. So that'd be what you can use there, and you can just use rho instead of rho times g, because there's a couple things going on with that. But it's just easier just to use that for your density and not have to worry about density times gravity. Somebody asked about the units earlier. You can keep track of the units. And let me run through that unless there's some more questions here. Okay. Let's see. So the units here are rho are 62.5 pounds per foot cubed. So you get a feet cubed in the denominator of this term. Well, let's take a look at what happens with these other terms. So let's see. When you calculate the radius, that's in feet. And then when you square it, you got feet squared. dy is the thickness, so that's in feet. So now you got feet squared times feet, that's feet cubed. And then the distance here is feet again. So if you look at that, you've got feet, feet, and feet twice. You got feet to the fourth power. But if you have feet to the fourth power in the numerator and feet to the third power in the denominator, these three are going to cancel with 3 from up in the numerator. It's going to leave you with 3 of them in the numerator, or 1 of them in the numerator, and then pounds is going to be left over as well. So you'd end up with feet in the numerator and pounds in the numerator, and that's what our answer is, foot pounds. So you can keep track of the units if you want. For most people, it'd probably be more work than it's worth. And I suppose if you're building satellites and things like that for NASA and you want to be really careful, maybe you want to keep track of the units. But most people just hope that everything works out good and give me an answer. It's up to you. Okay. Any other questions on this one? Well, not that you've been working hard, but maybe it's a good place for a break. So let's stop here.